And thanks for taking the time to join us today. What I'm going to do today is just sort of briefly talk about the Advanced Propulsion program and maybe give a bit of a sales pitch as to why the Advanced Propulsion program might be interesting. And then we're going to take a dip into some of the opening sections of a course on the MSc program called Pack Engineering, which I teach in term two. So this content is actually taken directly from the lecture, and really speaks to the motivation around the concept of advanced propulsion and the concept of electrification, and some of the things that we need to consider when we move into more detailed design, which you may do should you join the program. So, as an opener, I think it's worth sort of highlighting why advanced propulsion might be interesting to you. Okay, so electric vehicles are increasingly being deployed across the world. So that's both in sort of Europe and the US, and in the Far East. But increasingly, we're seeing more advanced electric vehicles moving beyond the kind of four seater vehicles. We're seeing a lot of two and three wheel vehicles being adopted in India. And we're seeing the early onset of the electrification of flight. It's a really challenging area to electrify, but we are seeing companies looking at electric vertical takeoff and landing vehicles, and using fuel cells to sort of power aircraft, and using electrochemical methods as the primary propulsion method. Um, but whilst we're seeing the widespread deployment of these vehicles, there really are quite significant challenges, ranging right away from design and manufacture, through to ensuring the longevity of the devices and making sure that they basically last long enough to allow vehicles to enter the market. And clearly, from the sort of performance and safety side of things, these are really vital considerations when you consider applications that people might be in. And more pressingly, when you start to think about combining a battery or fuel cell with the electric machines and the wider powertrain within the system, there's a lot of efficiency that could be lost if this is not done in a correct manner. So thinking about electric vehicle propulsion in a holistic sense, understanding the battery, understanding the electric motor, understanding the control system is really important. And this requires a broad multidisciplinary skill set and multidisciplinary approaches. Once you have that, then you're in a really strong position to be able to identify appropriate solutions for the application that you're looking at, be that road, be that rail, be that marine, be that aerospace. Okay. Um, and within the MSc in Advanced Propulsion, we really do cover all aspects of the electric powertrain. All of the program is delivered at the new UCL East campus. So this is the Marshgate campus. It's right beside the Olympic Stadium in Stratford in East London. And it's also hosted in the sort of program is hosted within the Advanced Propulsion Lab, which is a genuinely state-of-the-art, world-leading research facility for batteries, fuel cells, hydrogen more broadly, and electric machines and motors. To give you an overview of these facilities, so the facility is on the eighth floor of the building. We have some spectacular views looking out over London. But within there, we have all of the sort of standard kit you would expect to find in a university research lab. So things like battery cyclers and a range of characterization equipment. But we have some really neat specialized equipment as well. So in the center here, you can see a pilot line. This is for manufacturing batteries. What that means is that we're able to manufacture batteries in a similar manner to the large companies who are doing this, your CATLs, your BYDs, your LGs, your Panasonics. We're able to run very similar processes, obviously on a much scaled down version, but we're able to do this in the lab, and that allows us to innovate around various aspects of the manufacturing process. You can also see a range of environmentally controlled chambers, so we can look at high and low temperature operation, high and low humidity operation of these devices, and really test how a battery will behave once it moves out into the real world, and we can simulate the real atmosphere. I think the jewel in the crown of the lab is a 100-meter square dry room, which allows us to really do some amazing work with next generation devices where materials might be air and water sensitive. Within the dry room, we're in a much more comfortable environment and we're able to work with much larger systems. So all of these facilities are available for students to use in their research project, which occurs during term three, so over the summer of the program. So the program itself is really for students who want to get expertise in batteries and fuel cells and electrical machines. It's for students who want to get a broad understanding of the wider powertrain. And there's an opportunity within the program to tailor your route. So you can look at a kind of general route where you can mix and match some of the optional modules we have, or you can go down one of the three set routes that we have. So that's with a primary focus on materials. So that's electrochemical materials and structural materials. You could go down an electrochemical systems route, so that's doing optional modules around electrochemistry and around pack engineering, or you could have a systems route where you look at advanced electrical machines and power electronics hybridizations and drives. And those sort of opportunities or decisions are things that would make in term one and take these modules in term two. Um, and genuinely the course material is extremely heavily influenced by the research that we undertake at the APL. What that means is that we have really strong with the research we have really strong industrial ties, and what that means is that those that industrial insight is transferred into the educational setting. So our students, we've seen great success in our students moving into industry from our first cohort, who graduated this year. So that's really the Advanced Propulsion MSc in a nutshell. So now we'll move into the sort of lecture segment now. And the first question really is, why do we care about electrification, right? There's a lot of things that we should care about. And the UN Sustainable Development Goals are a nice example of this, right? They highlight areas around poverty, around food poverty, health and well-being, gender equality, education, work and economic growth, aquamarine life and life on land, peace, justice, equality. All very, very noble things, all very, very important things. But what I would contend is that there's almost none of these sustainable development goals that can be achieved without electrification. Because without electrification, we will not hit sort of targets to mitigate global warming. We will not solve any of the challenges around the climate crisis. And ultimately, from my perspective at least, and feel free to disagree with me, I think that's clearly the outstanding challenge of our generation. So when we start looking at the Sustainable Development Goals, the affordable and clean energy is an obvious one for us to think about when we start to think about electrification. But actually, when you look across them all, things like climate action, have a reasonably tangible link there. But things like responsible consumption and production are very, very important, right? How do we make batteries and fuel cells and electric machines so that we maximize the resources that we're building? We need to think about recycling. We need to think about optimizing the manufacturing processes that we're using so that we end up making these devices last longer, be able to be reused, be able to be repurposed for different applications. For other things, reducing inequalities, there's huge opportunities that electrification can bring. In certain parts of the world, access to refrigeration and to light is very, very challenging, right? And if we have to rely on diesel generators to provide access to light and heat and refrigeration, uh, we are really placing a large challenge in terms of just transporting fossil fuels, burning fossil fuels, and sort of creating localized pollution. If we can replace those diesel generators with, for instance, a hydrogen fuel cell or a battery system, where we're generating hydrogen on site from solar power and producing genuinely green hydrogen, then we have a nice circular circular route to improve the life opportunities for people living in these regions. So it genuinely has a big impact on inequalities. And I think you can pick any single one of these, and there could be an argument made that electrification has a direct impact on improving the outcomes of these SDGs. Um, we have about 420 gigatons of CO2 left for a two-thirds chance of staying below 1.5 degrees of warming. Um, that's it. It's really not a lot of carbon left, right? When you think that we're producing somewhere in the region of 8 to 10 gigatons of CO2 annually just from transport. Okay, so very, very quickly, you can see how that 420 gigatons sort of drops off. So every year well, historically, every year we've seen this increase in carbon emissions associated with transport. We're accounting for about 37% of end use emissions, and that's an important point to raise. Um, about 37% of end use emissions coming directly from transport. So, with this trend for increased emissions, there's clearly a need for us to not only mitigate the increases, but genuinely to reverse the trend. Okay, we need to start thinking about reducing emissions. And what you can see in the plot here is that in 2019 and 2020, or sorry, 2020 and 21, the trend did reduce. Now that was associated with the coronavirus pandemic. We don't necessarily want to rely on something so significant to reduce the emissions again. So we have to do this in a much more sensible way. And ultimately, even though it's very, very difficult, this is actually one of the easier sectors to electrify. Doing electrifying things like steel making and cement making is extraordinarily challenging because of the ingrained nature of CO2 utilization and the embedded nature of it within those sectors. Whereas with transportation, we've seen the adoption of electric vehicles. We've seen that these vehicles work. So it's just a case of us speeding it up, making it better, and then beginning to think more broadly. So moving beyond the kind of 200 to 250 mile range electric vehicles that people may drive, but starting to think about what happens with 40 ton trucks. What happens with our rail network? So if we want to have isolated rail, for instance, for motorbikes, for two and three wheel vehicles, for aircraft, for marine applications. All of these things need to be thought about. But you can clearly see here that road is the dominant emission, and I think that is probably the first area to think about. Now, all of this is pretty stark, right? To say that we have 420 gigatons of CO2 left that we can emit before 2050 is a bit terrifying. But it's important to remember that change can happen. So this photo is from New York, and it was taken on Easter Sunday in 1900. And what you will see in this photo, if you look closely, is lots and lots and lots of horses. So in 1900, the primary mode of transport in New York City, in Manhattan, was sort of by horses. And just 13 years later, this is the same street on the same day, and you can't see any horses at all. So within 13 years, you can see the widespread adoption of the automobile. So this is driven by Henry Ford and by the Ford Motor Company when they released the Model T. It was a very a very successful product, and it was predicated entirely on improving production efficiency. Um, when we say that we have history, I mean, with electric vehicles, we really do have history. So in 1912, EVs were about one third of car sales in the USA. So this is a photo of a Detroit Electric Brougham. But to power this, we needed close on 550 kilograms of lead acid batteries. The maximum range was about 130 kilometers, which actually really isn't that bad for the time. You could only go 32 kilometers an hour. It's not particularly fast, but it was a perfectly functional electric vehicle. At the time, it was very expensive, right? So $3,700 doesn't seem that much today for an electric vehicle, but in today's money, that's somewhere in the order of about $115,000. It's clearly a pricey vehicle to use. Um, But this was, a very successful technology. We had one third of the sales being associated with this, and ultimately, what happened was the development of alternative technologies. It largely the sort of internal combustion engine was really really successful. So this vehicle ultimately failed because the batteries were not good enough, because things like lithium-ion batteries had not been invented, because polymer electrolyte membrane fuel cells had not been invented. And now we have the technology to revisit this history and to develop new systems. Incidentally, it's also worth noting that Henry Ford's wife, so the person who enabled the internal combustion engine in this photo, this sort of mass production of the internal combustion engine, his wife drove an electric vehicle, preferred the electric vehicle, said it was a more comfortable vehicle to drive. So, in this case, it's sort of quite clear, at least from my perspective, that Henry Ford's wife was the real brains behind that family, because um, we've seen now that electric vehicles are just fundamentally a better solution than internal combustion engines for a range of reasons, alongside the CO2 emissions. So alongside this history and alongside this kind of moral requirement, there is also a legal requirement to do so. So in the UK, by 2035, the sale of new petrol and diesel cars is going to be banned. That means that the internal combustion engine is dead to all intents and purposes, right? We are not the sort of any further development will not matter, because by 2035, which really is only around the corner, I mean, the design cycle of vehicles is in, this sort of 5 year type time frame. So by 2030, people will not even be working on vehicles with internal combustion engines. Um, that this sort of imminent deadline is really forcing us to move towards electrification, and forcing genuine innovation in the battery chemistry and the wider electrochemical powertrain in systems. And this isn't just in the UK. There's been similar timetables, give or take 5 years, been announced across the EU and the EEA. So Norway, for instance, are slightly more aggressive in their timeline. Within China and the US, it's a similar sort of timeline. In the US, it's a little more state dependent. But if we start thinking about this plot, and we sort of accept that this has to happen, we need to really start thinking deeper about what are the sort of questions that we need to answer. So if we take this plot here, we can sort of break it down into road, rail, shipping, and aviation. Um, and we can start thinking about what are the requirements of these sectors and how complex are these sectors. Okay. For instance, with road, maximizing the range might be a motivation. Maximizing the ability to refuel or recharge your system might be a key thing. Safety is clearly going to be important. But the things that you may not consider are that if I'm a car company, I want to manufacture, several different cars of similar footprint. So actually fitting my battery pack into multiple car models is really quite important for me. If I'm Volkswagen, I also own Skoda, I also own a range of other brands, and I want to be able to sell an ID.5 and a Skoda Kangoo and whatever else. Ultimately, I don't want to have to make 50 different battery packs for 50 different models. If I can make three for all of those different models and utilize them in different ways, and then I'm a much more efficient place to be. If I'm thinking about rail, for instance, the sort of applications that you might, or the aspects that you might want to think about is, really how quickly can I refuel or recharge my system? Okay, I might be on a platform for a minute, 2 minutes. Can I put enough energy into my vehicle to get me to the next platform? That is the one question that you sort of have to answer. And then you have safety as well, because ultimately all of these vehicles will have people on board, and safety becomes critical. In the case of aviation, it is the number one consideration. So can I safely deliver passengers, payload, whatever the case is, from place X to place Y? To do that, I'm going to have to get off the ground, which means I'm going to have a very, very light propulsion system. And currently, lithium-ion batteries, whilst they're amazing and the sort of developments are really very, very impressive, but they're just not light enough to be able to fly, say, from London to Rome, or from certainly from London to New York. The technology just simply isn't there at the moment, and we're doing a lot of research to look at new battery chemistries and new battery formats to enable aviation and electrified aircraft. But still some distance away. Shipping is really a really interesting side of electrification, because there's really sort of two segments within a sort of a shipping journey that are very, very different but very, very important. So the first is at port, and that is a place that you really do not want to be emitting, because what you end up doing is you end up polluting the city that's the port that's hosting the port. And there's been lots and lots of work done to enable large ships to be plugged in and to be sort of electrified at port. But then once you start moving, you're in a very isolated environment, and it can be quite a harsh environment, right? You have lots and lots of salt water. You can have very cold temperatures. You could have sort of violent motion across the sea. So thinking about all of these things are really, really important when we start to think about how we design an electric vehicle drivetrain. The other thing to consider, or some of the other things to consider, are the kind of geographic or the local considerations. So, in the UK, the country's what, maybe 700 miles long, maybe a little bit longer, but the sort of the standard drive that people do is maybe 15-20 minutes to work. Okay, occasionally you might want to drive from Land's End to John O'Groats. It's a sort of 12-hour drive, but it's nothing huge. If you're in the US and you want to go from California to Florida, or California to New York, or you're in Australia and you want to drive from Melbourne to Cairns or to Port Douglas, these are extraordinarily large distances. So thinking about the geographic and thinking about the local considerations for your vehicles are really important. I'm from Ireland, right? The longest drive you can do in Ireland, if the roads were good enough, is probably about 4 hours, right? You could cover north to south in 4 hours. So you don't necessarily want to be selling a car that has the capability to drive 1,500 kilometers on a single range. It doesn't make a huge amount of sense to design that. And generally speaking, people don't want to drive for 24 or 36 hours without interruption, right? People generally like to sleep. People generally like to eat, and they need to do other things through the day as well. So all of these kind of considerations go into how you design a car. And there are some overlaps as well. So, what are the similarities between road, rail, marine, and aviation? I mean, ultimately, you want your system to be as cheap as possible, because if I'm company X and I'm selling my battery pack or my fuel cell stack or my electric motor, if I can make it cheaper, then I have a competitive advantage on my competitor. It also allows, higher profit margins and all of the other good things that drive the economy. But there are really considerable differences between them. So things like, in comparison to say between road and aviation, the differences in safety requirements are really quite stark. And within the kind of broader pack engineering course, we would go into the specific requirements for cell safety and the designs around that. If we just sort of focus in on road, we could say that, broadly speaking, it's about three-quarters of all transport emissions. So it's the thing that, is the biggest nut to crack, and the one that ideally we should sort of primarily focus on. And it's been very reassuring that over the last number of years, there's been huge progress in this area. But when we start to think about what a requirement for our vehicles are, generally they're low cost. And when I say low cost, I mean in the context of all vehicles. So in the context of a mega ship or a very large plane, right? We're talking about units that are in the order of sort of tens to maybe low hundreds thousands of pounds per unit. Okay, yes, there are the hypercars that are half a million, £1 million, but broadly speaking, the majority of the market is in that sort of 10 to 100,000 pounds. They also are high volume. There's about 60 million cars made every single year, so we need to make at least 60 million battery packs every year. And in again, in the sort of broader context of vehicles, they have relatively short life. So, vehicles or cars generally are on the road for in the region of 10 years. That's probably the sort of median range. In that time, you may have three, four different owners. And those three, four different owners may have different expectations from your vehicle, but ultimately you want this vehicle to be able to last for a 10-year sort of design window. So these are the key things that you would sort of start out with when you were designing your battery pack. You cannot make a battery pack that costs £200,000 and put it into a vehicle that sells for £10,000. You can't make one that costs £30,000 and put one in into a vehicle that costs £45,000. There's a sort of a maximum limit of probably about 30% that you can afford to spend on your battery pack, and that clearly defines the price of your vehicle. We need to be able to handle sufficient volumes of batteries to be able to make these packs, to allow us to have the range that we design into our vehicle as well. So thinking about 60 million battery packs, that's all well and good, but if there's 10, if there's maybe 1,000 batteries in each of those, you very quickly move into very, very high numbers, 60 billion batteries that need to be handled, 60 billion individual cells that need to be handled every year. And within those cells, there will be defects and there will be challenges. And designing around these is a very, very important thing. So all of these factors are things that you have to consider when you're designing your vehicle. And you also have to consider a question of is all road created equal? And the answer to that is clearly no, right? A sort of a small Fiat 500 type vehicle will have a very, very different design requirement to a large 40-ton truck. You don't expect to be pulling 40 tons in a Fiat 500, right? It won't be able to do it. What it generally will be used for is for city driving, okay? For your sort of larger estate and sedan type executive cars. I mean, you might think about sort of medium and long range applications. You might think about motorway driving. For off-road vehicles, there's clearly a different drive cycle that's being used there again. For your truck, it's primarily going to be motorway driving, and then for your sports car, you might start to think about, going around a track or driving in a slightly more aggressive manner. So if we start to think about each of these individually, with city vehicles, generally you're going to be driving reasonably short range. The vehicles themselves are going to be, fairly low cost. It's going to be stop-start driving, so you're, hitting a red light, the red light turns green, you start again, you hit another red light, so on and so forth. And the vehicles generally are pretty small. You're not also going to have a huge amount in the boot of the vehicle. It might be just be your sort of weekly shop or whatever the case may be. Um, but ultimately, what you want to do is you want to make loads and loads and loads of these cars so that you can sell the cheap model, or in inverted commas, I should say, the sort of cheaper model vehicle. You can sell that in increased volumes. Safety, you will see, is important in everything. It really is a driving factor in design. For your family vehicles, you may want to increase that range. You maybe have a little bit more scope in terms of your cost. The vehicle can be a little bit larger, which means you can accommodate volumetrically a larger battery pack in there. You may have to think about things like motorway driving. You still have this high volume production requirement, right? There's still quite a lot of these family vehicles and SUVs made, but you then also have to move into the kind of additional extras that people expect when they're paying a little bit more for a vehicle. Things like air conditioning, things like, in-vehicle entertainment systems and all of these things, which take up a non-zero amount of power and need to be taken into consideration when you're designing them. For your heavy vehicles, your design is entirely around medium and long range driving. You can accommodate a much higher cost in these vehicles because you're selling fewer of them, so they are going to be more expensive. They're a larger vehicle, so again, you can accommodate more batteries within the sort of volume of the vehicle. And the other thing that you need to bear in mind here is that primarily this is going to be sort of traction driven use case. So your acceleration, the start stop nature of your driving, is lessened to a great degree. So you end up sort of primarily focusing on just delivering smooth power. Again, safety is a huge factor. For aerospace, safety is number one, and the weight of the system is sort of the second half of number one. So it's getting the vehicle off the ground, but safety is extraordinarily important. This sector is very, very challenging, but it does have the benefit of a really regular mission profile. So flying from London to Manchester or from London to New York, whatever the case may be, you know what to expect. It's not like driving through central London where there might be diversions, there might be red lights that you hit that you didn't expect to hit. You kind of have a much more variable drive cycle. You have a much more regular mission profile, which you can design to in the aerospace sector. And you also have extraordinarily stringent regulatory requirements, which you have to hit across the board. And then for things like the marine and the rail system and the rail sectors, the volume and weight of the system is very, very important. In marine applications, the lifetime's very important, right? These vehicles are designed to last 30, 40, 50 years. So you need to have a propulsion system that is commensurate with that or can be changed. As I mentioned previously, you have that corrosive environment in marine applications as well, which is something to bear in mind and something that is sort of often neglected if you sort of start from scratch. With rail, it's reasonably short duration if you're in urban environments, but longer duration rail. You're thinking of moving towards pantographs where you have overhead power cables. So then your battery pack can be much much smaller. So if we think about how an engineer might approach this, you can basically use this V curve, and this is pioneered in the sort of 1900s, where you go through a series of steps and you identify what you need to do to be able to sort of complete your project. So for any vehicle, you initially design a user requirement. So you will have an avatar of someone that you envisage using your system. If it's a city car, that could be, an 18-year-old getting their first vehicle. Or it could just be someone who wants someone who lives in a city and just wants to kind of have a car to pop around the place. If you're designing the equivalent of, BMW 5 Series, you probably have a different avatar in mind and a different use case. But by developing that avatar, you can then move into having into sort of putting numbers on what is the requirement for my system. So I can start to say, right, I need to hit a range of 300 miles and I need to be able to have, robust air conditioning in there and I need to have a lifetime of 100,000 kilometers and I need to have a safety profile that is X. All of these things really feed into the kind of requirement specification, which you can then take and step down into a high and low level design. So the high level design being the kind of broader system design, and then the lower level design where you move into the specific details of the different components and the different systems within your or the different subsystems within your overall system. So that would be that a cell within a battery pack, be that the thermal management system, the electrical control system, the battery management system, etc., etc., etc. And then you implement it. So you then go and build the thing. And once you've built it, you then go through a series of testing. So you start looking at the individual units or the sort of module subsystems and test those in isolation. You then bring those systems together and integrate everything and sort of test it in concert with each other and see what the impact of crosstalk and on a various sort of various connections within the system is. See how your system efficiency scales as you build the system up, And then finally, you move into your acceptance testing. And acceptance testing is usually done over the course of, a year, if not more. And quite often, in the Midlands, you will see uh, Range Rovers driving around, and they have really funky patterns on them. They're sort of they look like zebras. And they're the next generation of Range Rover being acceptance tested by employees of Jaguar Land Rover. These things are sort of common to see on the road, where you have the unique the unique livery on the vehicles. But that sort of broad V diagram is a really important tool to be able to go through and design everything. So if we start thinking about electric vehicles, what we have, the energy and the power density of the primary propulsion system. We have the cost of the solution that we've chosen. We have the recharging or the refueling options that we have. So in the case of an electrified of a battery electric vehicle, we have the recharging aspect. In the case of a hydrogen powered electric vehicle, we have refueling options. Clearly, safety is going to drive a lot of what we want to do. We have the broader balance of plant. So how do we get the power from the battery pack to the electric motor? How do we keep the battery or fuel cell cool? How do we provide hydrogen to our fuel cell? Do we need to worry about humidification of that hydrogen? Do we have are we taking atmospheric air? Are we filtering it? All of the kind of the individual complexities of the system need to be taken into account with the balance of plant. And then everything needs to be controlled and monitored. Ultimately, that is part of your sort of safety framework. Um, but it's also important to be able to tell someone that your power system is at 20% state of charge, or your fuel gauge is 20% full, because that can prevent people from just pulling over to the side of the road and not having any power. And then the step that I think is often forgotten about when you start to sort of talk to people who focus on batteries and fuel cells, particularly in a university setting where quite often things are done in a more complex manner because you're looking at specific aspects of the degradation or the safety modes of whatever you're doing. But the manufacturability is a very, very important aspect of what we're doing, right? If if you design a battery pack that is just extremely challenging to make, you are much more likely to have failures in there, and it will cost you more. So simplifying the manufacturability is extraordinarily important. And increasingly, we're seeing legislation come in around recyclability, so around reusing components within your battery pack and components within your fuel cell stack, and actually individual components within your cells in the system. So recyclability is a great way to retain value following the sort of end of life of your system, but it's also an increasing legislative requirement. So if we start to think about energy density and power density, energy really refers to the amount, energy density refers to the amount of energy that's stored in our device, and it can be on a per weight or per volume basis. So we can have what we call gravimetric energy density, which is the weight focused energy density, or we can have volumetric energy density, the volume focused metric, and these are given in units of watt hours per kilo or watt hours per liter. We can use other units if we want. We can use grams, tons, meters cubed, whatever the case may be. But conventionally in electrochemical systems, we use watt hours per kilo and per liter. Um, with energy, that is effectively the range of our vehicles. So if you want to sort of intuitively think about what's the thing that drives my that sort of drives my range, it's primarily the energy density that you have in your system. In contrast, the power density is how quickly you can use that energy. And we can think about that again in terms of weight, so on a gravimetric basis or on a volumetric basis. And we would have these in units of watts per kilo or watts per liter. And that governs our acceleration. So both of these are very, very important aspects from the sort of initial high level design of our electric vehicle. But they are limited by both design choices that we make, but also intrinsic factors within the devices that we're using. So within a battery, there are intrinsic reasons that we hit a given energy density and power density. Within a fuel cell, the case is similar. So if we look at a battery, the energy density in a battery is going to be governed almost entirely by the selection of the active materials. So if we have a lithium-ion battery and we have a graphite negative electrode, we will get no more than 372 milliamp hours per gram of capacity from our graphite material. So that means the capacity of our overall pack is going to be determined by the weight of material that we put down into our cell. Now, there are other things like the accessibility of that material, but fundamentally, the graphite electrode is the thing that limits the energy density of a lithium-ion battery. Moving beyond graphite is a really interesting research area and is something that we do quite a lot of here at UCL. Um, but for sort of commercial systems, graphite is clearly the dominant technology and will be for the next good few years. So, given that, we then need to think about how do we maximize the design of our electrodes. So, for a highly energy dense system, we want to increase the thickness of our electrodes, so we have a higher ratio of active material to the current collector that we have within our battery, the metallic element that our electrode sits on. And if we can increase that ratio, then we have a more favorable active material to inactive material ratio within our cell. We're going to increase our overall cell energy density. The type of packaging that we use in our cell is also very important. So we have three common cell formats: our pouch, our prismatic, and our cylindrical cells. With the pouch cell, we'll use a laminated aluminium housing, and that has some benefits, particularly around the lightweight nature of the cell. But if we use a steel casing, we will be able to have better sort of internal compression within our cell, and we'll also have a higher sort of safety window for our system. So using those steel cans that you often see in cylindrical batteries has benefits, but clearly steel is heavier than aluminium, and a steel can is thicker than a thin sheet of aluminium foil. So we're going to have a higher mass of inactive material within there. And then finally, how we put this together clearly has a big impact on both the volume and the weight of our system. So if we have our batteries spaced very far apart, we will need to have longer electrical connections in there. Therefore, we just have more stuff within our battery pack. That more stuff has a mass, so it will impact the overall gravimetric energy density of our system. Likewise, the increased space will result in an increased volume for the same total energy of the pack. So we end up in a situation there where we have a higher volumetric energy density. So ultimately, we want to design these as tightly as possible whilst retaining the sort of safety aspects and the thermal management aspects that are important for ourselves. For the power density, all of the previous points are important, but we also have the additional considerations of thermal management because ultimately we can only allow our battery get to a certain temperature that we can safely operate within. So if we keep drawing more and more and more power and we raise that temperature beyond our safe operating temperature, we're in a sort of an unstable region and we are much more likely to see cell failure. So we want to avoid that. So the quality and the size of our thermal management system has a big impact on the power that we can deliver from our battery pack. And we also need to think about how the cells are packed together and the broader sort of connectivity between those cells. So the wiring, the ancillaries, the bus bars and whatnot that are within our battery pack. For our fuel cell stack, the energy density, so the capacity and the weight the sort of range of our vehicle is ultimately going to be driven by the size of the hydrogen tank on our vehicle. And this is where fuel cells are very specific. We need to consider not just the sort of primary propulsion unit, the fuel cell itself, we need to consider the overall system. So what is the size, what is the weight of our hydrogen tank, and what is the efficiency of the system? And that's a design choice. It's where we operate on our polarization curve. We then have the weight and the mass of the overall components. So what are the sort of region or what are the bits the sort of tie bars that we're using in our system? What are the bipolar plates that we're using in the system? What's the compression system in there? Um, and also all of our gas handling and all of our sort of thermal management and water management systems as well have a big impact on the energy density. For the power density side of things, this is where actually we have a little bit more of a design opportunity. So we have, how are we managing the water production and the temperature management within our system? What is our triple phase boundary density? So the point at which our reactions are happening. Do we have lots and lots and lots of those points, or are they kind of quite isolated? We need to think about the mobility of the gases and the species that we utilize and evolve within our fuel cell. And clearly, the weight of the components, the choice of the operating voltage, and the concentration of the gases that we're using are very important as well. And we can look through lots and lots and lots of different technologies, and we can sort of identify specific energies, power density, cycle life, operational time frame, whatever the case may be. And we can plot these in a table like this. And you can see that different technologies are suitable for different uses. We can improve some of these things through engineering, but these are the kind of intrinsic limitations of our devices. And what I've shown here are a supercapacitor, a fuel cell, a lithium-ion battery, and then a lithium sulfur battery, which is a technology close to my heart and one that I spend a lot of time researching. You can see in terms of cycle life, we go from maybe 50 to 250 cycles in a lithium sulfur battery, right the way through to 100,000 cycles in a supercapacitor. So the amount of times that I can use this system is clearly, hugely different. Um, for my sort of power density, my supercapacitor is also extraordinary, right? I can deliver 10,000 watts per kilo. Um, in comparison to a fuel cell, that's what, three orders of magnitude higher. It's a no-brainer. But if you then start thinking about the specific energy of the system, the energy density of the system, the supercapacitor is in the sort of 1 to 70 watt hours per kilogram range, whereas the fuel cell is much, much higher. And what you see is the lithium-ion battery, and the reason it's been adopted in passenger electric vehicles so much, is that it has this nice balance of a reasonable energy density, a pretty good power density, reasonable cycle life, um, and the operational time frame. So where it's sort of best suited to be functional is in the window that you would expect for a vehicle, right? So you want to be able to deliver acceleration in a vehicle, but you also want to be able to drive for a sort of middling length of time. We can sort of look at these in a table, but actually it is often more interesting to sort of plot things on a plot. So this is what's known as a Ragone plot. On the x-axis, we have our power density in logarithmic scale. So as we move from left to right, we have a more powerful system. On the y-axis, we have our energy density. So it's as we move from bottom to top, we're moving towards an overall lighter system. And it's a really nice way to compare the energy and power density of devices. The important thing to note here is we're on a logarithmic plot. But when we have this, what you will see if you look at the units here is that the only difference is a time component. And that allows us to draw in these tie lines where we start to think about the length of time that we might want a system to operate. And that's a sort of an intrinsic part of the link between power density and energy density, right? It's how quickly we can deliver the energy. So these tie lines are really useful for identifying how long we want our system to work. And then if we plot the sort of comparative power and energy density for the systems, we can sort of cherry pick the best solution for our application. So these tie lines, very, very, very important. And we can begin to plot different systems on here. So supercapacitors, generally very, very high power density, but low energy density. So they sit down the bottom right of this plot. Um, with those sort of characteristic timescales of 3 to 30 seconds, you could think about these as a sort of acceleration aid. Fuel cells, on the other hand, much lower power density, much higher energy density. You're talking about longer term operation. So in a electrified context, that's range, right? That is it's operating your vehicle for a longer duration. And lithium-ion batteries sit in this sweet spot where they can operate for 30 seconds, right? You can discharge them very, very quickly and get high power out of them, or they can operate in a more smooth manner and last for several hours. And that is why, in essence, lithium-ion batteries have been deployed in electric vehicles. So with these Ragone plots, we can then also think about different applications. So in this case, aerospace. If we had a drone where we wanted to operate it for, a number of seconds, we might think about supercapacitors. If we had a small aircraft where we have, minutes of operation, we might think of lithium-ion batteries. Once we start getting towards 4 or 5 hours operation, we're moving beyond what a lithium-ion battery can do, and we need to think about fuel cells, or we need to think about next generation battery technologies. And next generation battery technologies are really important. So these are some of the performance targets which have been set by the Faraday Institution, which is the UK's national electrochemical energy storage funding agency, and an institution that we work extraordinarily close with at UCL. And you can see that from between now and sort of 2035, there is a huge drive to reduce the cost, so about a two-third cost reduction, to double the energy density of our batteries, to quadruple the power density of the batteries, to move towards inherently safe battery packs, to start thinking about the lifetime of our battery pack being the length of the lifetime of the car, and to start, considering some of the lower temperature operations that the lithium-ion batteries struggle in. And the key differences, I guess, really are in terms of the kind of predictability. So developing fully predictive models is a clear sort of area of research, and moving towards a fully closed loop recycling capability. For fuel cells, you can see the difference in sort of performance metrics here, and they are largely driven by cost. It's fundamentally the thing that's holding fuel cells back at the moment, is that they are just really expensive to operate and to buy as capital equipment. So you can see a lot of the drive here is to reduce the system and the stack costs. There is also clearly a benefit to increasing the durability, so the lifetime of the vehicle, and to increase the system efficiency. And also we need to think about hydrogen, right? With a fuel cell, we need to think about what's the system doing, but also what's the fuel that's going in. And by 2035, there's a desire to significantly decrease the cost of hydrogen. And these are targets that are set by the APC, which is a sort of a large council in the UK focused on automotive production. So that's really a sort of a quick intro to pack engineering. Within the sort of rest of the 10-week program that is pack engineering, there's kind of deep dives into device degradation, into safety, into how you sort of design a pack, what is the sort of fundamental design of the pack, and a wide range of aspects. And all of these details you'll be able to find on the Advanced Propulsion MSc website. I'd just also like to highlight there's some upcoming events. So the Postgraduate Open Day on the 25th of January, and the MSc webinar on the 29th of January. We also have a UCL East Open evening on the 12th of February next year. So if you are in London on the 12th of February, it will be great to see you, and we will be showing prospective students around the labs in Marshgate. But with that, I'd just like to say thank you very much for taking some time out of your day and listening to me speak. And if there are any questions, I'm more than happy to answer them. Thank you. Okay, I don't know if there are any questions. I'm just trying to stroll through them here. So one question here focused on hydrogen. So do the facilities in the lab include infrastructure for research involving the generation or use of hydrogen? They've worked in this field for 5 years. So yes, we have the capability to operate fuel cells. We have 2 fuel cell test stations that we're currently being upgraded to be sort of 5 kilowatt in scale. We're also installing a electrolysis system of about 1 kilowatt scale. So we have We have hydrogen in bottles, but we'll also be generating hydrogen on site, which we can then feed into fuel cells and test those fuel cells. Um, just trying to see if there's any more questions. No problem at all. Very, very happy to answer the question. There are no questions in the comments there. Oh, sorry, I've one in the Q&A. So it's talking about including perovskites into batteries. I mean, fundamentally, there are there's scope to include almost anything within a research setting. My primary area of interest in research is around battery safety and around next generation battery technologies. So we do a lot of work with lithium sulfur batteries. I co-lead the UK's national lithium sulfur research project. And we do a lot of work with industry, sort of looking at battery safety and optimizing battery safety. This sort of incorporation of new materials is covered by some of the other academics who would teach on the Advanced Propulsion MSc program. So I think it's probably best to wait until you arrive in September and discuss it with them. Uh, Last, do I have any views about PFAS regulations and the challenges that they might pose within batteries? Yeah, PFAS regulations are going to be extremely challenging if they sort of go through as they look like at the moment. Fluorine is present in broadly speaking every battery. So within the binders, in the context of next generation batteries, it's a really promising material to use to mitigate some of the dendrite growth within lithium metal electrodes. Fundamentally, we're just going to have to innovate, right? If these regulations come into place and we can no longer use fluorine, we have to use something else. In answer to the question about is there any related research at UCL on this topic, yeah, we have lots and lots of active material of active research looking at the use of, for instance, amino acids and proteins in next generation battery technology. So using those devices as binders. A lot of our manufacturing work, we're focusing on using aqueous systems where we're using sort of rubbers and non-fluorine containing components as the binder in a battery, and that will substantially improve the sort of challenges associated with PFAS, so with the presence of fluorine in batteries, but it remains a challenge. And with fuel cells, fluorinated membranes are de facto the sort of the components that are being used. There's clearly going to be a need to consider new solutions there. I think that's all of the questions that we have. So I've just noticed we've run over time by a couple of minutes. So again, thank you very much for joining today, and I look forward to seeing some of you in person in September 2025. Thank you very much. Bye bye.